The purpose of this mini lecture is to introduce the concepts that we need in order to study light as a wave. So just as background, so far we've studied the ray model of light, and that was perfectly fine for predicting image formation in lenses and mirrors. But now as we consider items on smaller and smaller length scales that are closer to the wavelength of light, then the wave properties or the wavelengths of light become more important. And so we need to look at the wave model of light. So one thing that's going to play an important role is phase difference. So remember that waves can add and subtract through interference, if you remember from Physics 120. And so the phase that they add at is very important. Is it half a wavelength? Is it a full wavelength? Is it a part of a wavelength? That'll all depend or determine if those waves add constructively or destructively. We'll talk about that more in a minute. So in this whole section of light as waves, we'll study interference, diffraction, and specific experiments of two-slit interference and one-slit diffraction, and then a diffraction grating, and talk about spectroscopy, and then also polarization. Some other applications that we'll look at are thin films, and then resolution of optical instruments. So in this particular lecture, I'm going to talk about dispersion, and then the idea of superposition, as I said, adding waves, and then the importance or role of path length. And then I'll introduce Huygens principle, and then the two-slit interference problem. So just a little motivation for studying things, just a couple of examples of the importances. One is resolution. How well we see things depends on diffraction. So we'll see how that works out when we talk about optical instruments and resolution. And then also diffraction is a way to disperse light, or in other words, separate light into the component wavelengths. So let's look at the idea of dispersion first, and then look how we could accomplish that first of all with a prism. And then we'll eventually return back to the idea of diffraction as a way to disperse light. So if we look at visible light, for example, and dispersion, if I have, say, a piece of glass, say, I can look at this graph and I can see what the refractive index is as a function of wavelength. So we can see that the refractive index is going to depend on wavelength. We look at these equations over here. So notice that the index of refraction is equal to the speed of light divided by the velocity of the light in that material. So this is the speed of light in a vacuum, and this is in the material. So if I look at that and then I realize that the speed of light, though, also is equal to the frequency times the wavelength. Then I can combine those and see that the index of refraction is indeed dependent on these things. So if I look at here at flint glass, then over here in the violet, I have an index of refraction about 1.66 or so. But then if I look over in red, at those wavelengths, the index of refraction goes to 1.61 or so. So light, violet light, will have a higher index of refraction, or will refract or bend more towards the normal than red light. And so because of this differential bending of light or refraction, we could separate or disperse into the different wavelengths. So here's an example in a prism. We have white light coming in, which is all the light combined together. And if I were to draw a normal here, actually it's not quite as straight as it could be. So if I have the normal, notice I have my incident angle or theta 1 in, and then theta 2 is going to be different depending on the wavelength of light, and red gets bent much more, or excuse me, violet gets bent much more than red. And so you can see that the light gets spread out, and because of the geometry, that spreading gets accentuated over here. An example of this in nature is a rainbow. So if you imagine a droplet of water, that droplet is going to refract light. So incoming you have sunlight, and then the violet gets refracted more, it's bent more towards the normal than red light. Over here you have total internal reflection, and then again you have refraction back out. But now at this point the light has been separated out. The wavelengths that are red over here are entering our eye from the droplets that are higher up. But then because of the difference in angle, the droplets are lower down, this red light doesn't hit, it misses our eye, but it's the violet that we see. And if you imagine all the droplets in between, you would have different wavelengths that make it to our eye. And so the result is we see a rainbow. So this idea of dispersion doesn't just happen in prisms and index of refraction. It also happens with interference and diffraction patterns. And so what we'll see is that the interference of light, how they add, depends on the wavelength. It's wavelength dependent, and we'll see that eventually with the equations. And so if we look at this, these are, what are we looking at here? These are patterns. Whenever I have green light, then this is just one wavelength, so we call that monochromatic. And then over here, whenever we have white light, then it's a mixture of all wavelengths. So notice that you see like little inklings every so often at different places of separation into a rainbow of colors. We can see here very nicely that we have this, what was originally white light gets separated into different colors. So we'll talk more about how that works. But these are the images that you might see with interference and diffraction. So let's take a moment to talk about superposition of waves. So remember from Physics 120 or the last physics class that whenever you have two waves that are at the same place at the same time, then they add. And we call that superposition. And they add exactly place per place. So say here I have this wave up here, the red wave, and here at the amplitude is +1. Over here the amplitude is +2 on this blue wave. Then if they're in the same place at the same time, then I'm visualizing separately, but we suppose they're at the same place at the same time, then they would add together 1 + 2, and this would have an amplitude of +3. And any point on the wave, that's going to be the case, that this amount for the red adds to the blue, and then we'd get that amount for the purple. And here we have 0 + 0 gives you 0. So that's superposition. And most times these two waves are not in phase, and you don't get an exact total adding, constructive or destructive, but those are the cases that we're most interested in. So just as review, constructive interference is when you have two waves that are in phase. So in phase means that they match up, they're in sync, wavelength per wavelength, and when that happens, they add together and you have a total that is greater than each of the original amplitudes. So in other words, if these each had an amplitude of +1, then this final wave would have an amplitude of +2. If they are, however, out of phase by half a wavelength, so right here, notice that if I were to trace these waves, this one here, here's one wavelength, And if I shift over by half a wavelength, I see that that wavelength is right there. They have the same wavelength, but they're out of phase by half a wavelength. They're just shifted. When I add piece by piece, then I have a +1, -1 here, 0, and these, you can see everything's going to cancel. And so the result is you have no wave. They're going to exactly cancel, and that is destructive interference. So in the case of light, when you have constructive interference, it's going to give you a bright result when you add those two. And then when you have destructive interference, then you're going to get dark, or there's not going to be any light there. So when we're talking about interference of light, what we're going to look at situations where the path length is, or the difference in path between two sources of light is important. So looking here, suppose I have source 1 and source 2. So these are my sources. And the light coming, if I look at, say, if I'm at point A and the light coming out from, 1, and the light coming out from 2, that is the same path length. So I know that if they started in phase, then these two will add constructively. So in other words, if they start in phase to begin with, then they'll end up adding in phase, and you would have constructive interference. Ooh. Okay, however, if I'm off at another point over here, so let's say that I'm going over to point D, then I can see that the path length is very close, but if I were to actually measure, there's going to be an additional path length right here. So there's a difference. Now, if that difference happens to be lambda, one wavelength, then these two waves will still be in phase. Even though there's a difference in path, it's going to be the same. But if there's a difference in phase of lambda over 2, then that extra path length, that extra half lambda, is going to make everything shift, and they're going to be out of phase, and we're going to have destructive interference. One other principle before I come back to that idea of difference in path length is Huygens principle. And that is that every point on a wavefront acts as a point source. So what does that mean for our experiments? I'm going to skip to here. If you suppose that we have parallel rays coming in from a faraway source, and that means that the wavefronts of light, for the wavelength, is going to be perpendicular to that. When the wavefronts hit a barrier and then there's a slit with an opening for that light to go through, then every point on each of the wavefront is going to act as a source. So now when you had all this light coming in, you now have 2 point sources and the 2 point sources can emanate light that is going to interfere. So let me introduce Young's double slit experiment, and here's how it goes. Young took a piece of cardboard, essentially, made 2 openings or 2 slits, very small, very close together in this cardboard, and then shone the sunlight on it. And the question is, what would you get? Well, normally we would say, well, there's 2 apertures, and so we're going to get 2 lines on the board, which is what you might expect. However, if these are very small and close together, you don't get that. You actually get a pattern of interference. And so what I'd like to suggest is that you, and this is the schematic of what happens, but after viewing this video, take a look at this video that recreates the original Young 2-slit interference pattern.